the topic ring theory. So we had the definition of ring. So for defining ring, we need two binary operations. So that binary operations are addition and multiplication. So here it satisfies three properties. The first property, capital R is a abelian group under addition with 0 is the identity. The second part is capital R is a semi-group under multiplication. Third property says distributive property holds A dot B plus C equal to A dot B plus A dot C. So if any one of the non-empty satisfies these three properties, we can conclude that capital R is a ring with addition and multiplication. So after that we have defined here, so commutative ring. Commutative ring, suppose A dot B equal to B dot A. Under multiplication it is commutative means, so we can conclude that it is a ring with commutative property holds. So then zero divisor, what is zero divisor we have defined? So suppose taking two non-zero elements, multiplying that two non-zero element, we are getting the answer equal to 0. So that is A is not equal to 0, B is not equal to 0 implies AB equal to 0. So this is called a zero divisor. So then the definition of integral domain. So for defining integral domain, so we need a commutative ring with identity. So after that, it has no zero divisor. There is no zero divisor element means we can conclude that it is an integral domain. So and also we need the definition of field because we are going to solve problems now. So we are going to apply the definition of field, the definition of ring, everything. So here the definition of field says a commutative ring with identity. So again, so here all the elements having multiplicative inverse. Then we can conclude that it is a field. So finally, we have defined a homomorphism of a ring. So last class, the last topic we had seen that homomorphism of a ring. So for defining homomorphism, we need a map. So we have taken the map F from here. So the map is F from two ring. So R comma plus comma dot to another ring S comma plus comma dot. There are two rings we have taken. So we have taken a map between R plus dot S plus dot. After that, two property holds, two conditions satisfies. So what are the conditions for proving the given function F is homomorphism? See here, the first condition is F of x plus y equal to F of x plus F of y. Second condition is F of xy equal to F of x into F of y. So if any one of the map F satisfies these two conditions, we can say that it is a ring homomorphism. It is a ring homomorphism. So based on ring homomorphism, we have problems. So the first problem, see here. So the first question is, it's actually F, the map F from Z to 2Z. F from Z to 2Z. So here they have defined F of x equal to 2x. So F from Z to 2Z, F of x equal to 2x. So here you are going to prove F is a ring homomorphism. So how you are going to prove it? We are checking each conditions. So take the first condition. We are going to prove F of x plus y equal to F of x plus F of y. The second condition, check it, F of xy equal to F of x into F of y. So if any one of the two condition, any one of the condition fails means we can conclude that F is not a ring homomorphism. Yes, so here the definition is important. F of x equal to 2x. In the particular problem, they have defined x from z means 2x from 2z. Like that they have defined. So here we check it, first one. So take it F of x plus y. Left side, take it. Left side we are proving F of x plus y. So you are going to prove which is equal to right side F of x plus F of y. So consider F of x plus y. So F of x plus y, how we will write it? See here, the definition says F of x equal to 2x. Suppose F of x plus y comes, what will write? 2 times of x plus y. 2 times of x plus y from the definition. So this is equal to multiply it. So 2 into x, 2x plus 2 into y, it is 2y. Okay. So now again 2x can be written as by using the definition, it is f of x plus 2y is f of y. 2y is f of y. 2y is f of y. So now see here, we have proved f of x plus y is f of x plus f of y. So first condition is true. Now the second condition, just to take it left side, f of xy. So you are going to prove this is equal to f of x into f of y, f of x into f of y. So here by the definition f of x comes, put it 2x. F of xy comes, you have to put 2 times of this function, this variable, 2 times of xy. So here, see here, 2x into y, 2xy can be written as 2x into y. 2x places we can put it, it is f of x. But y, we can't put it f of y, because f of y means f of x is 2x, f of y comes, we are putting it is 2y, f of y. So we can't write it as f of y. So f of xy cannot write f of x into f of y, cannot be written as f of x into f of y. Therefore, the second condition fails in the particular problem. So therefore, the map f from Z to Z is not a, f is not a ring homomorphism. So this way we are finding whether the given map is homomorphism or not. So now let us see the second problem. So these problems I gave you to you, the same material through WhatsApp. So again the second problem is, so here I am taking f from. So f from capital R to capital R. This is the second problem. Map is given f from R to R. Here the elements are, capital R elements are a plus b root 2. The elements are in the form a plus b root 2. A comma b belongs to set. So again they have defined the map as f of a plus b root 2. Answer is a minus b root 2. A plus b root 2 is a minus b root 2. So this way they have defined. This is the question. Okay. So f from R to R, f from R to R is defined by f of a plus b root 2 equal to a minus b root 2. So the question is prove that f is a ring homomorphism. F is a ring homomorphism. So after that they asked to find onto. You have prove. They asked to prove f is onto. So first to prove that the map f is a ring homomorphism. So for proving ring homomorphism, now it is okay.
Okay, ma'am.
Okay, ma'am. So for proving f is a homomorphism, we are checking that two conditions. First condition, take it f of x plus y equal to f of x plus f of y. So find out the left hand side. So considering left hand side, f of x plus y equal to, so here a plus b root 2. So therefore here only one element, after taking one element we are getting a minus b root 2. But here see that two elements are there. So before considering f of x plus y, so you have to write what is x. X is write it a plus b root 2. Then y, it is c plus d root 2. Take it two elements. So just to take it, x is a plus b root 2, y is c plus d root 2. So now here find out x plus y. We need f of x plus y. So before that just calculate x plus y. Adding this, so see here a plus c plus b root 2 plus d root 2. A plus c plus b plus d root 2. So this is x plus y. So now find out f of x plus y. So therefore f of a plus c plus b plus d root 2. So just to take it, f of x plus y is like that. So this is equal to, so see here now f of a plus root 2 element. F of a plus another element is root 2. So that is f of a plus b root 2 comes, you have to write a minus b root 2. So therefore, by using the given definition, a plus c minus b plus d root 2, right? So root 2 coefficient, put it minus after taking f. So here the real part like that, a plus c, the same answer, write it. So then square root of 2, the coefficient is, put it minus. So now again rearrange it, because we are proving now f of x plus y equal to f of x plus f of y. So therefore rearrange it, a plus c minus b root 2 minus d root 2, multiplying root 2 inside. So now combining a and beta, so it is a minus b root 2 plus c minus d root 2. So now again see here, this is equal to a minus b root 2 can be written as, by using the definition. So see here, f of a plus b root 2 is a minus b root 2. So a minus b root 2 comes, you can put it, it is f of a plus b root 2. So therefore by using the definition, so writing f of a plus b root 2 plus f of, this is c plus d root 2. So a plus b root 2, what we have taken, a plus b root 2 is, it is x.
Yes.
It is x. So this is equal to f of x plus f of y. F of x plus f of y. So see here, so you have proved the first condition, f of x plus y equal to f of x plus f of y. The second condition is f of x y equal to f of x into f of y. F of x y equal to f of x into f of y. So like that. So see here now. So x we have taken, x equal to a plus b root 2, y equal to c plus d root 2. Second condition for proving this, f of xy equal to f of x into f of y. We are proving like that. Okay. So before considering f of xy, so find out what is xy. So xy, this is equal to a plus b root 2 into c plus d root 2. Multiply it. So this is equal to a into c, ac, plus a into d root 2, ad root 2, plus bc, plus bc, square root of 2. Again bd, b into d, root 2 into root 2, you can write it, it is 2. It is 2, root 2 into 2.
Ma'am, note konja right side notunga ma'am. Telugu theriyala.
Here now?
Okay ma'am.
Okay ma'am. So again combining here, root 2 terms separated, the remaining terms write it separately. So AC, last term is plus 2BD. So AC plus 2BD plus second term, square root of 2 is common. So square root of 2 into AD plus BC. AD plus BC. Okay. So see here, it is xy now. It is xy. Then find out f of xy. So f of this element AC plus 2BD plus AD plus BC into square root of 2. So what is f of a plus b root 2? In the definition, f of a plus b root 2 comes. So a minus, what ma? Not seeing now. So f of a plus b root 2 is a minus b root 2. So this is equal to, right? This is equal to AC plus 2BD minus, put it, AD plus BC into root 2. So then, again take it separately because we are proving that f of x into f of y. So this is equal to, see here, AC, okay, AC plus 2BD minus AD root 2 minus BC root 2. So again here write it AC plus 2BD. So this is actually minus of here, right? So AC plus 2BD. So here, this is the answer for f of xy. So now find it, f of x answer. Okay, so we are proving here f of x into f of y. So for checking that f of x answer calculated, this is equation number 1. Take it like that. So it is f of x. F of x is f of a plus b root 2. So this is equal to a minus b root 2 by the definition of f of x. Then f of y is equal to f of c plus d root 2. So this answer is c minus d root 2. Multiply it now. This f of x into f of y is equal to a minus b root 2 into c minus d root 2. Here this 2 multiplication. So f of x, we are proving that f of xy equal to f of x into f of y. F of xy we calculated already. Right side also we are going to find it. Then we are going to prove left side and right side are equal like that. Okay. So again multiply it. This answer is a into c, ac minus a into d root 2 minus bc root 2. Then root 2 into root 2 is 2. So plus 2bd. See here, the first answer AC plus 2BD, this answer. Again, the second answer is also same. Therefore, we can conclude it f of xy equal to f of x into f of y. F of xy equal to f of x into f of y. So see here, we have proved the two conditions in the particular map f from capital R to capital R. So the first condition we have checked f of x plus y equal to f of x plus f of y. The second condition is we have proved now f of xy equal to f of x into f of y, f of x into f of y. So therefore, so we have proved, we have checked all the two conditions. We have checked the two conditions. So therefore, we can conclude that it is a ring homomorphism. F is a ring homomorphism. So this way we are proving. So we have one more problem. So now the third question is, so question is prove that the only idempotent elements of an integral domain are 0 and 1. This is the question. So question is prove that the only idempotent elements of an integral domain are 0 and 1. So we know that what is idempotent? Idempotent definition says, so a square equal to a. Yes, a square equal to a, idempotent or boolean. So a into a star a equal to a. For define, when we define no group, that time we have used idempotent element means a square equal to a. So here also the only idempotent elements of an integral domain. Integral domain definition says it has no zero divisor. It has no zero divisor. So idempotent elements can be written as a square equal to a. So a, take it in the left side. So a square minus a equal to 0. So a is common. So I can take it a minus 1 equal to 0. A minus
Ma'am,
1
paper
equal to
கொஞ்சம்
0.
ரைட்ல
What ma?
நோட்டை கொஞ்சம் ரைட்ல நோட்டுங்க மேம். ஓகே மேம், ஓகே.
Okay va?
ஓகே.
So a into a minus 1 equal to 0. So therefore, here the possibility, before taking the possibility, whether we take the possibility a equal to 0 or a minus 1 equal to 0, always When we have like this, a into a minus 1 equal to 0, we can write it immediately, a equal to 0 or a minus 1 equal to 0. But see here, we can write it. How we are write it? See here. Here, idempotent elements of an integral domain. In the problem, they are given idempotent elements of an integral domain. Integral domain means it has no zero divisor. So therefore, so here by using that, a equal to 0 or a minus 1 equal to 0. Therefore, a equal to 0, a minus 1 equal to 0, answer is a equal to 1. So therefore, we have proved now the only idempotent elements of an integral domain are 0 and 1. 0 and 1. Okay. So this way we are proving the particular given problem. So now the fourth question I gave you, give an example of a commutative ring. Give an example of a commutative ring with identity which is not a field. So which is not a field. Field definition is we know. So just to recall it, a commutative ring with identity has a multiplicative inverse. Multiplicative inverse is there, means we can say that it is a field. But the question is, you are going to give an example of a commutative ring with identity, but it is not a field. So commutative ring with identity, it has no multiplicative inverse. If you say like that, so you can conclude that this example is not a field, like that. Okay. So see here, we are taking the example is here, z comma plus comma dot. Z comma plus dot is a ring. Yes, we have proved z plus dot is a ring. When so actually in general Zn comma plus comma dot is a ring, we have proved when n is a prime. When n is a prime. So here Z plus dot is a ring with identity. So what is the identity here? So 0 is the identity. Okay. So here multiplicative identity is 1 because 1 into 1 equal to 1. 2 into 1 is equal to 1. 3 into 1 is equal to 1. Yes. So here this is the identity element. 1 is the identity element of in multiplication, under multiplication. So here, so see here, we are going to check whether it has a multiplicative inverse or not. So see here, 2, just to take the element 2. I gave you that example. 2 belongs to capital Z, right? 2 belongs to capital Z. But see here, 1 by 2 is the multiplicative inverse of 2. 1 by 2 is the multiplicative inverse of 2. But 1 by 2 is not belongs to Z. 1 by 2 is a rational number. Okay. So rational number is not belongs to the integers. So therefore it has no multiplicative inverse. So like that, every element of Z has no multiplicative inverse. So therefore we can conclude that this example is not a field. This example is not a field. So Zn, Z plus dot is a commutative ring with identity 1. Even though it has identity, but there is no multiplicative inverse. Therefore, it is not a field. This way we are proving. Okay. So these 4 problems I gave it to you. So again, the next last definition of this chapter is integer modulo n. Integer modulo n, just you know the concept, right? So for example, so 5 is congruent to 1 mod 2, like that. Okay. So 5 is congruent to 1 mod 2. So you know that this concept, so 5 is divided by 2. 5 is divided by 2. The remainder is here 1, like that. Okay. So 5 plus 1 or 5 plus 1, like that. The same concept only, we have the next definition is integer modulo n. Integer modulo n, the same concept. So just a definition alone we have it. Okay. So till this we are completing the first chapter. Okay. So after that the next chapter only. Next chapter is just extension of the first chapter. Okay. So the first chapter, just recall it. So here algebraic system we have defined. Algebraic system has 2 parts. One is group theory, next one is a ring theory. For defining group, so we need only one binary operation. So in that we have defined semigroup, monoid, subgroup. So based on that problems, after that we did many theorems, then normal subgroup, Lagrange's theorem, fundamental theorems on homomorphisms, all that we did, the first part. So the second part is a ring theory. For defining a non-empty set is a ring means we need two binary operations. The two binary operations are addition and multiplications. So after that we are checking that. So here three conditions. Three conditions are R plus is an abelian group with identity 0. Second condition is R comma dot is a semigroup. Third condition is distributive law satisfied. So this is the ring definition. So after that here, next definition, zero divisor, integral domain, field. Then we did the theorem based on field. Every field is an integral domain. Then every finite integral domain is a field. Like that, we did all the theorems. So finally, we did the definition of ring homomorphism. What is ring homomorphism? So by based on that, we did the problems. So finally, the last definition is integer modulo n. So till this, the first chapter is over. So after that, the next chapter is not a lengthy chapter. It is a short only. So here, just based on the ring theory, so we are doing the second chapter, just extension of ring theory. So we have the second chapter. So from the second chapter also I gave you the material. Yes, the last class, last day. So I gave it to you. So we'll continue now. So the first topic. So before that we just recall it. So which is the portion of the second chapter. So I'll give you now.